Okay, I'll start sharing my screen. It's already been our tradition to kind of start with spending a few minutes showing these couple of slides. So this is the last in this series of coffee talks in this semester, and if you will, these have been sort of pilot meetings. I think we will scale this program up toward the next semester and advertise it more broadly throughout various schools, both in our within the space science community, but also outside of it, including various engineering schools and so forth. So if you guys have any, actually questions will come on the next slide. So if you go to this link, if you haven't been there before, there is a little registration button. And if you register there, you'll get added to our list where we will email various opportunities as they come up that might be of interest to undergraduate students. So today we have our esteemed panelists, Alexandra, Matiella, and Novak from Johns Hopkins Applied Physics Lab, and Kevin Pham from the National Center for Atmospheric Research, High Altitude Observatory. And the host today will be Sarah Vines, who is a scientist also here at Johns Hopkins Applied Physics Lab. So I'm sure it's going to be an interesting and exciting discussion, just like we had the other two times. So here are some useful links. If you want to screenshot this, feel free to do that. The top one is the link to this series that I just showed to you. This is the page on our website on the Center of Geospace Storms that's sponsoring these meetings. There are quite a few student opportunities there, and also recordings from these meetings are also posted there if you want to go back and listen to the ones that you maybe didn't attend. And I can actually see on YouTube that they get quite a number of views. So people are coming back afterwards and watching them. And then there are some opportunities for undergraduate students that are listed on these websites at Virginia Tech, at the Johns Hopkins lab here, and also at UNCAR. There's quite a few opportunities, but if you have any questions or you want to know more about any of the things that you see, feel free to email any of these folks here. I'm the last one here. The professors representing the three schools that are participating in this activity are also listed here. Feel absolutely free to email any of us. And well, rules of the road is probably doesn't matter because we don't have that many people, but we will go until about 4:30 or so with the panel discussion, and then questions and answers for 15 minutes or so. Again, we don't have that many people, so if you have a question, feel free to just unmute yourself and shoot. Okay, I will stop sharing at that and give it to you, Sarah.
Yeah, sweet. Yeah, we'll go ahead and get started. So like Slava said, I am Dr. Sarah Vines. I am a space physicist at Johns Hopkins Applied Physics Lab. And so today, yeah, we have Dr. Alexandra, Matiella, Novak, and Dr. Kevin Pham. So actually, I think I'm going to start by opening the floor up to Alexandra, if I may. Can you just first start by describing your career path and kind of what inspired you and drove you to go down this road?
Sure, yeah, thanks. So hi everyone, Alexandra, Matiella, Novak, coming to you from Maryland, where APL is. So I'm a planetary geologist at the lab, and I have a PhD in geology, and so a little bit different topic than a lot of the scientists that we've been hearing through these series, but still very much space science related. So I have been interested in geology even before I knew what geology was and something you could study. As a kid, I really liked being outdoors and being in nature. And I loved rocks and minerals and all that fun stuff. And when I was young, we lived in Colorado for a while, and we used to take a lot of road trips around the Rocky Mountains, and we used to do a lot of trips. I had family in Tucson, so we used to do a lot of road trips to Tucson too. And I just remember always along the way of these road trips, seeing really cool geology and being inspired. And the desert is the best place for geology because there's not a bunch of vegetation covering everything up. So just being exposed to that as a kid, and then I think being inclined towards science and liking math and science, I just knew that I wanted to study natural science, basically. Didn't know quite yet that it was geology, but always knew as a kid I wanted to study in natural science and be outdoors. I wanted to work outside. So when I got into undergrad, again, I knew I wanted to study science, but I wasn't sure exactly what yet. And I had not declared. I was a sophomore, I think the beginning of my sophomore year, I was still not declared for a major, but I was taking all the requisites for a physical science major because I knew I was going to get a physical science. I just didn't know what. So I was taking all the math and chemistry and physics classes. And then when I came across these brochures listing majors one day, and there was a geology major, and that was in the Department of Earth and Space Sciences. And when I read the description, I thought, well, that's exactly what I want to do. I want to major in geology and study Earth and Space Sciences. So I ended up going into the department and just, loving it. I love geology. It's very hands-on. A lot of times we'll lecture during the week, we'll learn the principles, and then on the weekend, we would go out and go camping and be out in the field and applying the principles, what we learned in the classroom, out in the field. So it was just a great experience. And then while I was in grad school, I realized I really wanted to study volcanoes. And I was fortunate to get a internship at the Hawaiian Volcano Observatory after I graduated from UCLA, is where I got my bachelor's. Go Bruins. And while I was at the Hawaiian Volcano Observatory, I knew I wanted to eventually get my PhD in geology to study volcanoes. I wanted to be a volcanologist. I applied to grad schools while I was at HVO, and I got declined from 2 and waitlisted at 2 others. So that was really devastating because it definitely knocked me off my path that I had set for myself. But luckily, while I was there was someone that was telling me that they were still accepting graduate students at Michigan Technological University. And so I ended up applying there and getting into this great program where I use satellite imagery to study volcanic ash clouds in the atmosphere. And so then that set me up for eventually coming to APL. We do all, the planetary geology we do is all using spacecraft data. So learning how to study geology with satellite data on Earth for active volcanism and volcanic ash clouds in the atmosphere set me up really well for being able to do geology using spacecraft data throughout the solar system, which is what I do here at APL. So I haven't had a very straight path. I didn't know, like when I was an undergrad and I wanted to study volcanoes, that I would end up being a planetary geologist or volcanologist one day. But those were the opportunities that presented themselves to me, and I'm really fortunate to be here at APL because there's so many different projects to be involved in. So I'm actually involved in a lot of planetary geology projects here at APL. But yeah, that's basically my story. So
yeah, no, I think you touched on something really important, that a lot of us have really meandering paths, and it's sometimes it can be incredibly hard to deal with something that you had your mindset on, but then because you never know what really cool thing actually falls into place afterwards. So thank you for sharing that. So Kevin, to you now, how did you start out in your interest in science and land at NCAR?
So in high school, I had this really interesting physics teacher who liked to joke about everything. And probably the thing that really convinced me that I wanted to go into science was he would do this every year. He would try to show that a bowling ball would fall as fast as like a golf ball. and he would drop it in the same place. And he was already past retirement. He was just coming back, and he kept dropping in the same place. So this year, when he dropped it, he decided to go through the floor into the basement, and it shattered like this giant display case. But that got me interested. It was exciting. So I was like, oh, I want to figure out, what's going on, how things are going, and how the world works. And I also was okay at math. I wasn't the greatest, but it was something I could do. So as an undergraduate, I didn't really know what I liked. I just knew I kind of liked physics in general, but physics kind of incorporates everything. And you read about all the different science news, and you go, oh, this person discovered this person discovered this, but they'll generally say, oh, this was an astrophysicist or this was a geologist, right? But you don't know that, oh, this person was actually a volcanologist, or somebody who studied black holes. You didn't know what their specific subfield was. You just kind of knew generally. So as an undergrad, I just kind of took physics and kind of floated along. I didn't know what I wanted to do. I would just talk to a professor and be like, hey, what do you do, and what is and one thing that I learned as an undergraduate was, when you go talk to a professor, don't ask them what they do, because they'll just show you the latest results and then they'll make it sound like the most exciting thing in the world. You should ask them, what is the process that they do to get that? Because the first thing I did as an undergraduate was a particle physics lab. And it sounded interesting. You learn about particle physics and things like that, and you get to work in a lab. So I went, and what he had me do was, I had these giant blocks of lead glass, and I spent 2 years polishing it. Because what they did was they would shoot the particle beam through that, and then you would get Bremsstrahlung radiation. But so it sounds exciting. Oh, you shoot a beam of particles through, you get Bremsstrahlung radiation, and you measure that. It sounds exciting. You learn a lot of physics, but the actual work involved me standing in front of a grinding wheel, grinding this block of lead glass for 2 years. So that wasn't the most exciting to me. But so I did just talk to a whole bunch of professors, and then try to ask them what kind of work they did, and things that got interesting. So I got interested in computer simulations and computer work, but not so much as an undergrad. I kind of learned about it. Going to graduate school is a little bit different. I applied to a lot of schools, but I wasn't really committed. So I just applied to a bunch of schools, got a lot of rejections, and I just said, hey, I'll just take a year off. And then I was visiting family in Texas, and there's a university in Texas, Arlington, which is close to Dallas. And so I went to the university there. I talked to one of the professors there, and I asked him what he did. So he showed me this cool 3D simulation, and then with 3D glasses, so you get to fly through the magnetosphere and things like that. And I was like, oh, this is pretty cool. How did you do this? And he sat down and actually walked me through what he did to get the simulation. And he goes, are you interested? I said, yeah, this seems pretty interesting. The semester has already started. I didn't submit any application. I didn't even know the school existed. And then he said, okay, how about starting now? And then he pretty much enrolled me. He walked me up to the department office and enrolled me right then and there, and then said, are you free next summer? I'm going to fly you to Boston. I'm like, great. I have no idea what you're doing, but great. But that kind of got me started. And then the more I got into it, the more I liked it. So it wasn't really something that I planned on. It's just something that I stumbled upon, and then it worked out.
That's awesome. Yeah. I understand that experience about like, oh, you think this is going to be great until you start actually getting in the nitty gritty, and you're like, oh, okay. So I will say, yeah, I think you're underlining just the importance of having a chance to get to do actual like lab work and research as you go through undergrad and grad school years. So actually, starts getting into a nice segue, Kevin, about the kind of work that you're doing now. So if you wouldn't mind talking a bit more about what you are researching now, and anything else that you want to talk about for that, as far as like why it's important, how it matters, and then if you had any other slides, now's a good time to bring those up too.
So let me bring that up.
Yeah.
All right. So kind of similar to my path towards getting a PhD was I wasn't committed to any particular field or topic. So in a similar way, I'm not committed to any particular region of geospace. So geospace has a whole ton of regions, and within the region, so you have the magnetosphere up here, the atmosphere down here, but then within each region, you have a lot of sub-regions, so that you can split the atmosphere into neutral parts, you can split into ions and charged particle areas, and then the magnetosphere is up here. And then in each section, you can split that up into a whole bunch of subsections, and then each subsection has its own specific physics, its own model. You can, so there's a lot of little pieces of geospace, and kind of similar to my path, I didn't commit to any one of these. So what I do mostly is I try to couple and combine a whole bunch of these regions together. So this simulation you see on the right, play the movie. So this is the Earth. You're looking down on the northern pole on the left and the southern pole on the right, and these are satellites that are flying through. And so you can see I've run simulations of these, and by coupling all these regions together, each one with its own different model, you start introducing a lot of effects, and you can see all these waves coming out. These waves that are coming out are due to the magnetosphere coupling back and feeding the upper atmosphere, and then it generates these waves that come out and start flowing through the atmosphere. And so I do a lot of things in which you try to compare satellites, which are just these one single point measurements that fly through space, with the whole simulation, which is these giant 3-dimensional and even more larger simulations, and then you try to match them to the data to make sure that you're getting all the physics right, or at least the physics that that are there. And then you try to figure out, okay, what physics are missing. If I'm missing, for example, you'll see these peaks right here. The red curve is missing these peaks. Well, these peaks kind of indicate that we're missing a lot of physics and a lot of things. And then you go back to the drawing board and then you go, okay, which region am I missing? How do I get that region, and how do I combine that into the rest of the model? And then how do you make this model even bigger and more complex, but at the same time you include a lot of physics and a lot of interesting things. So that's one of the things I do. And then related to this, going a little bit slightly more detail, is if you look at the high latitude region, you have two different ways for the magnetosphere to couple with the atmosphere. So one way is through these magnetic field lines that go in. So along the magnetic field lines, you can get a lot of currents that flow through. So these currents will enter the high latitude region, like the polar cap, the northern pole and the southern poles. Currents will go in and start heating the region. When you start heating the region, you expand. So when you heat something, you start expanding it. When you expand the polar cap, a lot of the particles in the polar cap will get heated, they get charged, and then they can escape the polar cap and then flow back into the magnetosphere. So it's not just a one-way process, it's a two-way process, and then you get a lot of things that go back and forth between them. So you get a lot of currents that go back and forth, you get a lot of particles that go back and forth. It's just a lot of things going back and forth. And so including and looking at all of this together is my area of interest. And then it's trying to figure out, how do the different regions communicate? So before, what people would do is they would only care about the currents going in and the currents going out. They don't care too much about what the particles do. So more recent work that I'm doing is looking at, okay, when you have currents and things going in, what is the number of particles going back out, and how do these particles coming back out interact with and impact the magnetosphere? So those are things that those are things that I'm doing right now.
And I will say, I really like that diagram of the coupling region in that high latitude atmosphere with the currents and magnetic field, because you're touching on a subject that I enjoy. All right, so I want to turn over to you, Alexandra, and hear about some of the work that you've been doing and why that's so exciting for you and for other people as well. So.
Sure. And I also have some slides, so I'm going to have a little bit of different area. We're going to be we're not talking about so much space physics and things happening in and around our space as much as things that happen on the surface of these planets and geology with rocks. So again, my background is mostly in volcanology, and so I'm actually one of the main project. I'm involved in a lot of different projects, but one of my most exciting projects that I work on the most right now is looking for evidence of explosive volcanism on Mars. And so this slide shows this area on Mars called Arabia Terra. And there have been previous research has suggested that there's these huge calderas, like Yellowstone caldera type volcanism in this region of Mars. And if that's the case, then we would expect to see large volumes of volcanic ash deposited throughout this area, the same way we do see large volumes of volcanic ash associated with Yellowstone caldera, which last erupted about 600,000 years ago. And just to note also, I'll talk about this a little bit too at the end, but this right here is the Jezero crater where Perseverance landed for the Mars 2020 landing site. So that was a really exciting recent space exploration success that we just had. And it was fun because I actually got to help out with that mission a little bit, doing some of the science planning through the mineral instrument that we have on board the Mars Reconnaissance Orbiter. So go to my next slide really quickly. I'm going to talk to these slides really quickly, but basically the CRISM instrument we have on board the Mars Reconnaissance Orbiter looks at the mineralogy of the Martian surface. And so right here we have a CRISM image of this area on Mars. It's basically two craters, and this is a false color image right here. So north is pointing up, and these two round features are two craters. And if we take a cross section of these craters and compare it to a digital elevation model, we actually can see layering of this mineralogy. And these particular types of minerals, these colors right here that we're seeing, give us spectra. And so on the CRISM, there's CRISM spectra and there's lab spectra. And basically what I do is I match them up. So I know what a certain altered mineral looks like in lab spectra. And if I'm seeing it in the CRISM spectrum, this image of the surface of Mars, then I can be pretty confident that that mineral likely exists in that surface. We're seeing that same spectra. So this is a part that I had to learn. I'm not a spectral person. I'm a volcanologist. I'm not a geochemist or anything like that. So I actually had to work with other people to learn how do I identify these specific types of minerals. I knew what minerals I was looking for. So minerals like ammogalite, allophane, and montmorillonite are here on Earth, very commonly associated with altered volcanic ash, explosive volcanic ash. So I knew what minerals to look for. I just needed to know how to identify them in this particular data set. So we did this in a few locations around our study area, Arabia Terra. And we were actually, if you can just go back really quick so we can match up this black outline right here of the fretted terrain is also this black outline here. And so we have these suggested calderas, these little red spots. And so in planetary geology, we can also compare our observations to models. And so that's what we're doing right here. Back in 2013, an author, Kerber et al., did a model of what volcanic ashfall deposits would look like if they were originating from these calderas over here in the more northwest region. And so they modeled what the ashfall would look like. And then we were able to compare those in this bottom graph with the observed ash thicknesses that we're seeing in our mineralogy data. And you can see it, the model and the observations actually, they're certainly close to each other to be related to each other. We're not so far out of the end members here. So it's kind of cool to actually see, oh yeah, we can actually see the ash that we're modeling might be there. And of course, I can't let you guys go without showing you pictures of rocks on Mars, because that's the best thing. But I just wanted to mention really quickly, I saw this picture and I got really excited because there is a lot of debate out there whether you can actually have explosive volcanism on Mars. A lot has to do with the atmosphere. You kind of need a certain type of atmosphere for things to degas and erupt into the atmosphere. So this picture right here shows these really cool rocks in the foreground. And this is from Perseverance. And Perseverance did land next to what they think is a volcanic ash fall. And so then when you see these rocks here, I'll just show you really quick. This is what a piece of pumice from Earth looks like. And then you have rocks that look very similar to that right around where Perseverance is. So it's just really cool to see those very familiar features that we see on Earth, and we understand how they got here on Earth to see those on other planets. And then you can start thinking about the geologic processes on other planets. So studying all of this is really going to help us understand more the geologic history of Mars. And that will actually tell us a lot about the geologic history of our own planet. Because if you think of Mars, Mars is kind of on a fast track of evolution ahead of us of where our planet might be going. So understanding more of the geologic history and evolution of Mars can give us some forward-thinking insight into where our planet is going as well. So that's that. And now you guys saw rocks. So
yes. No, it's really cool. Well, because then I think you bring up some really interesting things about not only about understanding our own geologic history, but also understanding histories of, once you do start having more exposure and you start losing some of your atmospheres and your magnetic fields, and what happens to surface weathering, which is not just at Mars, but at the moon, at other bodies. So there's such cool stuff that you can learn from rocks and beyond. So I do want to kind of, sorry, go ahead. No, please.
Well, I was just going to say for human exploration as well, like going to Mars or going to the moon, it's so important to understand space weather in terms of human exploration because of the radiation that the astronauts can be exposed to.
Yeah. So, and that's also such a great point. I do want to kind of ask both of you then another question. And I think you both touched on this in different ways, and maybe you can expand upon this a little bit. So thinking of people in undergrad and starting to think about grad school and thinking about your own path, what do you think is kind of the most important things to consider as far as how, if you are interested in pursuing this kind of science path and going further into some kind of science grad school or other kind of like related field, what kind of experience did you find to be kind of key here? And so Alexandra, I'll go ahead and open that up for you.
So I think for me, the most important thing I did as an undergraduate student was made friends with the graduate students and figured out with them what kind of opportunities were out there and looking for work as close to me as possible, because you're an undergrad, you're really limited where you can go for work. Maybe you don't have a car, or maybe you just don't have a lot of time to get off campus. And so the first place I looked for work was in my department. Mm-hmm. I didn't go and apply for, competitive research opportunities outside. I just looked inside first to see if that was what I knew was going to be most accessible to me. So if there was any opportunities available, that I would have an easier time getting those opportunities. And I was able to do some work for graduate students who were doing research. They had funded research. They had a little bit of money they could share with me to help them do work. And what I ended up doing was crushing up rocks into a fine powder. They would go out in the field and collect rocks and bring them back to me. And I would crush them up into this fine powder to get them prepped for a mass spectrometer. But it was like really super cool, fun work. And so that was, I think, what something I did really well was looking for the opportunities that were right next to me.
And so for you, Kevin, what would you think as being kind of good experiences to try to go for?
So I would suggest just talking to everybody, talk to other undergraduates who might be doing some work, and then talking to the professor or graduate student that they're working with. Talk to graduate students, talk to professors. A lot of professors are very open, even if they don't have any students. Even if they say they could be the most difficult professor in the world, and if you go talk to them, they will find something for you to do. As long as you're interested, they'll find something for you to do. I had a good experience with a professor who was in theoretical particle physics. That sounded really difficult. And as an undergraduate, the math was well beyond me. So I went and talked with him, and he's like, okay, here's a simple integral. Solve that for me. I spent like a year on that thing, and I was like, I can't do this. And he goes, oh, don't worry. I wasn't expecting you. I already did that. But it gave me the opportunity to work with that and to go, oh, that's actually not as bad as I thought it was. But just talk to everybody, and then especially talk to the department office. A lot of the office ladies will know everything. They'll know who has money, who has leftover money, who has open spots. Go talk to them. They know everything.
That is true. Okay, so thank you both. I want to go ahead, and we have time now to kind of open the floor up for any other questions that anybody has. So please feel free to go ahead and unmute yourself and ask, or raise your hand, or drop it in the chat. I do have one to ask as well, if I can start off. So this one actually is for you, Alexandra. So thinking back for the Martian system, at which point was it do we think that it was actually volcanically active, and was it globally volcanically active, or were there just kind of hotspots? Because it's not like there's not tectonics in the way that we have it, right? Okay, yeah,
right, yeah. So a lot of volcanism on Earth is tied to plate tectonics. Like, for example, the volcano in Iceland right now. Iceland sits on top of the Mid-Atlantic rift, so the volcanism originates from that huge spreading rift going right up through the Atlantic Ocean. But no, there's no tectonics on Mars. Or it tried to have tectonics, which is how you ended up with that big Valles Marineris feature. That was an attempt at plate tectonics, but Mars cooled off too easily or too quickly to continue the energy needed for plate tectonics like we have on Earth. However, the biggest volcano in the solar system is on Mars. It's Olympus Mons. And so, yes, at one point, Mars was very volcanically active. Probably a lot of, even more so than Earth is today. Earth is right now the most volcanically active planet. But it certainly has been hundreds of millions of years, we think, since there was, the last eruption. But there is volcanoes all over Mars. There's lava flows all over Mars. And like I said, the biggest volcano in the solar system, Olympus Mons, is on Mars.
Very cool. Okay, I have another question coming in for Kevin. So you were showing that nice figure about the high latitude region. So does the ozone level in the atmosphere, what does that depend on as far as like space weather and other kinds of big events? How does that work? Can you talk about that more?
So specifically the ozone layer. So the ozone layer depends on both a lot of activity that comes from down below, but then as far as space weather, you can also get radiation belts, very highly energetic particles that will penetrate everything that's above the ozone, and it'll penetrate all the way down to the ozone layer and then start ionizing a lot of the more neutral gases there, and then it'll generate ozone as well as deplete ozone as well. So it's a complex process, but you can get a lot of energetic particles from geospace going down into that region.
All right, and then I've got another question in the chat for you, Alexandra. Are two magma chambers suggested as the source of the Martian lava flows in your research, similar to Yellowstone, or is that kind of up for debate?
So it's definitely hotspot volcanism, and that was the other answer to your question. It's not volcanism related to tectonics like it is here on Earth, but hotspot, which we do have. Yellowstone is hotspot volcanism. Hawaii is hotspot volcanism. So we know it's hotspot volcanism, but as far as how many chambers or how big the chambers, that's definitely up for debate. The reason we can characterize those things so well on Earth is because we have a lot of seismic data of the surface underneath Earth. And Mars, we do not have hardly any seismic data. The only seismic data we're getting right now is from InSight, which is one sole little geophone, and it's really hard to get an idea of the densities and the depths of things when you only have waves coming and going to one thing. So, so we're not sure about what the magma chambers look like underneath, but it's definitely hotspot volcanism like Yellowstone.
That's neat. Okay, so I have another question coming in to you, Kevin, and actually it's related to one of my own. So what is the biggest simulation you've run? How long did it take, and what supercomputer, or how many clusters?
Let's see. The biggest simulation that I've ran, it's not as big as some of my other colleagues, but let's see. To think about it. So the biggest simulation I've ran runs at about 4,000 cores or so. So that, in terms of computer clusters with the latest and greatest, that's like a good 13 computer clusters or so. So it's not a huge amount, but it's still a good number.
As kind of like a related one, I'm kind of curious so I've never really worked with simulations ever. And I find folks who do modeling kind of like magicians in a certain way. What was your first programming language, and what do you normally program in?
My first programming language was Visual Basic. It's a Microsoft program where you don't have to
Nice.
type anything, you just move boxes around and then it generates a program for you. That was my very first programming language. After that, I was interested. A lot of it was just I learned on my own. You just Google search everything, and there's code that exists for you, and then you just kind of read over and go, okay, I need to change this number, and then it does exactly what I want. And then over time, you kind of pick up a lot of things.
I actually got Visual Basic for DOS off of eBay version 1.0.
You guys have thrown it back. Whew. All right. So I have a question in the chat. So for both of you, so I'll start with Alex and then I'll ask you, Kevin. Which undergrad courses turned out to be the most beneficial, and which ones do you wish you could have taken?
So the most beneficial, it's hard to pick because I really liked all my classes. Obviously my geology classes ended up being the most beneficial, but outside of geology, I took a few writing classes, and even as a graduate student, I took writing classes, writing specifically for the public. And I think that actually helped out a lot as scientists. It's really important for us to be able to communicate our science, not just with each other, but also with broader audiences as well. That's getting much, much more important these days. The class I had wished I had taken was, I never took an astronomy class. And I really wish I had taken an astronomy class. I didn't imagine myself ever working out in, space sciences, but even just as a matter of learning about your environment, I wish I'm a big advocate of learning about your environment through geology classes. You can do that through your astronomy classes as well. So I do wish I had taken an astronomy class.
Yeah, super fun. And so how about you, Kevin?
So the most beneficial undergraduate class that I took was, it wasn't really, I guess it was a class. It's more like a seminar. So you would sign up for this class that changes every semester. And what happened was that class would have a specific theme. For example, it would be space. So you would have both the astrophysicists and space physicists, and then that class would have something on the order of about 15 students. We would split that into two groups, and then you would join a lab for a week. And you would just do their work for a week. And then the next week after that, you join another lab and do work for a week. So you get a lot of hands-on experience to figure out what they do, what can you do, and whether you like the actual work that you do. Because the results are only, you only see the results for like 5 seconds, and then the work takes months and years to do. I wish I took, unlike Alexandra, I wish I took more writing and communication classes. If people don't know what I'm doing, it doesn't matter what I'm doing.
Yeah.
You need to be able to communicate that everything you're doing is extremely important, and that everybody should give you millions and billions of dollars to do the work.
True. No, you touched upon a big thing of like, how key like publications, grants, communicating to our broader public. So doing things like press releases. I think I was always kind of surprised just by how much we write and how much even crafting a paper is storytelling in its own sense, right? So yeah, no, you guys touch on some really great things. All right, so I want to open up any other further questions, comments from anyone. Okay, well, excellent. Well, I just want to thank you again, Dr. Matiella Novak and Dr. Pham, and thank you all for joining us for today. As Slava said, please feel free to go to the links that he showed from the slides earlier, contact him and our other senior professors that were listed on the sites for this event. There are a lot of opportunities both at our individual institutions and more broadly in space science, planetary science, physics. So if there's anything else, please feel free to contact us. So,
and we will do more of these. We know this is the end of the semester, so you'll have other things to do. But
right.
we will continue afterwards. Thank you very much, guys, for your interest. I think
thank you all.
Bye.
Bye.
Bye, thank you.
Bye.
Thank you.
Thank you.